Ask, give me the excuse letter, okay, or some kind of evidence. If you go to funeral, take a picture to show that you are in the funeral. Okay, so I have something to as evidence to show that you are that dead. Otherwise, I think it's true, but think about this: if I don't check it, okay, and there are some students try to get away with that. Just send an email, go to the funeral. I never know, so I need evidence. If you go to any meeting, show me some evidence for that, okay? Last time we finished the tank battery, question for that. No question about that. Today we will try to finish the compressor, okay? For compressor, I think you have seen several big compressor and vapor recovery unit already. Have you? You have seen vapor recovery unit. Okay, the vapor recovery unit on the East Campus is reciprocating compressor type. Okay, when we have gas come from the well, we may heat it. We have line heater, right, for gas production. For oil, we don't need line heater. Line heater is for prevent what? Hydrate. You know that, right? You're about to have the exam on like Thursday after next. So you should know all this. Okay, we heat it, it's high pressure. We may cool it if it is very prolific well. If it is very hot, we cool it. Then we treat it, remove all water, and then do some kind of gas processing and sell it. Okay? Or we may need compressor inside. And when it go through processing plant, it have to go into a cross-country gas pipeline, very big gas pipeline, right? So if you want to move from here to Louisiana or to New York or somewhere very far away, we need compressor. The compressor that you have seen at CSI is gathering station of cross-country pipeline is very big. It's not quite the one in VIU unit. Okay. So this lecture we will talk about the theory part. So we have separator, wellhead, compressor. Let's say we have pressure of 200 psi. Gas pipeline is at 1000 psi. If you want to sell to that gas pipeline, you have to increase the pressure somehow. To increase the pressure, we use compressor. Okay. So we go up from 200 to 1000 psi. The overall compression ratio is 5. 5 comes from 1000 divided by 200. Okay. Compression ratio of 5 is too much for single stage. And we talk about that why it's too much. So here's a compressor. When we have incoming gas in, it go to separator or scrubber to remove any liquid. It go into compressor, we compress it, and we may have to cool it down and compress it again. Okay. Theory of compression, we can have isothermal compression. Isothermal means constant temperature. Okay, isothermal. That was in the quiz last year about isothermal thing. Okay. We cannot really have isothermal compression. You know, when we compress gas, it getting hot, become hotter. Okay, so to have isothermal compression, that is like ideal case. We have to compress it slowly and attach it to some kind of heat sink. So we control the temperature. We have heat transfer all the time to maintain the temperature. So for PV equal to constant, okay, that is isothermal compression. It works for ideal gas. Okay. Isothermal compression, so the word is isothermal is constant temperature. Another one is isentropic compression. Isentropic is constant S, constant entropy. Okay? It is reversible adiabatic process. Reversible means it can change back. Okay? Adiabatic process means no heat transfer in and out, no heat loss, perfect insulation. That's adiabatic. I have a box, no heat coming in, no heat coming out. The compression inside is reversible, so it's reversible adiabatic. Or it is isentropic compression. Okay? This word, isothermal isentropic compression, you memorize it. Okay, for isentropic compression we have PV to the power of K equal to constant. Okay. This K, some book use kappa. Okay. It is the ratio between Cp and Cv. Cp is specific heat for the case of constant pressure. This is specific heat capacity for the case of constant volume. So PV to the power of K equal to constant. If we have this, it is isentropic process. Cp of air, okay, Victor, I just asked you because I need your help. Cp of air is about 0.24 BTU per bar mole per Fahrenheit. What is Cp value in the unit of BTU per bar mole per Röntgen Victor? Same thing, very good. This is probably the exam, okay? Very good. What if I change from that to BTU per bar mole, but this time I put Celsius? Want to try? Basma. So Cp of air is 0.24 BTU per bar mole per Fahrenheit. If I change to BTU per bar mole per Celsius, will it be more than 0.24 or less than 0.24? It cannot be the same. It won't be the same. More or less. This time I change from Fahrenheit to Celsius. More or less. I don't need a number, I just want to say no, more or less. More. What's that? Okay. All of you have to be able to answer this kind of thing in exam, okay? Basma, let me change the question. How much is typical value for Cp of water in the unit of BTU per bar per Fahrenheit? Not bar mole, bar mass. How much? 1, right? What does it mean? The temperature, the heat required to increase the temperature of water, of 1 bar of water, up by 1 Fahrenheit is 1 BTU. Okay? If we need to heat it up by what? 1.8 Fahrenheit. We need more heat, right? So 1 Celsius, is that 1.8 Fahrenheit? Is it 9 or 5 something? Yes. Okay. Delta T of 1 Celsius. Delta T of 1 Celsius equal to 1.8 Fahrenheit, right? The increment in temperature. So if I change this unit, instead of per F, I change it to C. The unit of C have kind of bigger gap. We require more heat to raise the temperature up by 1 Celsius. You agree? Do you? You didn't say anything. Let's hear what you say in the exam. Theoretical compression. Value of specific heat is Cp over Cv. Roughly, it is more than 1. Okay? For air, it's 1.4, argon 1.66, 1.66, 1.141, 1.4 something. It's about 1.4 something. It can change with temperature and pressure. And I add one more slide. So those of you who downloaded already, may not have this slide. I just added this morning. So this slide show the value of K, ratio of Cp over Cv, of pure methane, CH4. If I have pure methane, what happened? I run the webbook from NIST. Okay, if you go to NIST webbook, we can do some kind of quick calculation. So I run it. I ask webbook to generate Cp value of methane at a constant temperature from 0 psia to 5000 psia, and the ratio is like this. It goes from 1.3 up, maybe about 1.8 or something. So it changed with pressure. Now I ask to do a constant pressure but change temperature. So when I increase temperature at 100 psia, K value go down like that. So it changed from 1.32 to 1.24 or something. It changed with temperature pressure. Okay, and if you want to know what exactly it is, you either use a chart, handbook, or that website, NIST website. Okay, I'll just Google it. NIST website is very reliable, so I use that. So that I give you some kind of typical value. Your part of the work is you have to know that it is more than 1. Okay? So if I ask you, Cp over Cv, is it more than 1 or less than 1? You should be able to tell it's more than 1. Alright, we have several kind of process when we do compression. We can have PV to the power of n equal to constant. N may be 0, n may be 1, n may be k, n may be infinity or something. So if n equal to 0, so this means P equal to constant. Constant pressure process we call isobaric process. Okay, memorize this name, isobaric process means constant pressure. So if n equal to T, then we have PV equal to constant. Like PV equal to ZnRT, right? So when T constant, PV equal to constant. That is isothermal process. Isothermal process is constant temperature process. If I have P, V to the power of kappa, okay, equal to constant, that is isentropic process or constant entropy. Okay. If we go to infinity, this means P, the change in P doesn't matter much or something. So we call constant volume process. We don't have constant volume process, but just to give you a name, that's called isochromic process. Constant volume, this means we didn't compress it at all. Okay, we don't have constant volume process. I review all this to you because the reason for today is eventually we will do some derivation and try to get this equation. That's the objective of today. Okay. With this equation, what we can tell is how big should be the compressor. If I know what kind of gas, intake pressure, discharge pressure, I should be able to tell how many horsepower do I need per million standard cubic foot. So I want to buy a compressor. I cannot just say I want to buy the compressor. Actually, if I tell CSI my discharge pressure, suction pressure, what kind of gas, they just, and flow rate, what kind of flow rate, they just give me, hey, you need to buy this big compressor, maybe 100 horsepower or something. And we believe that it is correct, but they don't tell you anything else. They just give you, hey, you buy 100 horsepower. Just that. So why do we have to learn all this? We want to check if it is right or not. What they tell you, is that right or not? Is it in the same order of magnitude or not? Okay? You don't just want somebody else to tell you what to buy, right? You really want to check, is that what I need? Okay? And if you be able to do the calculation too, you can tell them, hey, I think your calculation is okay. Most of the time it is. Like 95% of the time it is. But sometimes in some company may oversize a lot for you. It can happen. It's not all the time. That's why I want you to know this. Alright? So that's the end product. How do we design a compressor? Alright, that's the name of the process. Now, how does it work? If I have recip unit, reciprocating compressor, reciprocating motion is back and forth motion. Okay. When I have reciprocating compressor, let me show you PV diagram. Pressure and volume. We start at point 1. Okay. Valve close, that valve close, that valve close, and we have cylinder full of gas. Okay. It is at low pressure. So we have low pressure but high volume. That is at point 1. Then I start my compression process. I compress it. I push, use some force to push it. I move my piston from that position to another position. My valve still closed, okay? When my valve closed, I push it. What happened? Volume go down, but pressure go up, right? Pressure go up. I close the valve and I push. When I reach point number 2, okay, I'm done with that. So I open the valve. I open the discharge valve. So I'm ready to send my gas that I compressed out to the next unit. Okay. So I open my discharge valve. Then I still push the piston, move from that point to the new location. So when I go from 2 to 3, the discharge valve open, just the discharge valve. So I push, 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 and push. So I release gas at the constant pressure. I take it, put it out. Okay. So volume go down, but pressure remain the same. Then I start to pull my piston back. When I'm about to pull it back, I close the discharge valve. I close this suction valve. So when I pull it back with everything closed, I have some volume. So this gap is the volume in this part. Okay, that is this gap. Okay, so I close everything. It's kind of I put a vacuum or let it expand. Okay, I let it expand when everything closed. So when I let it expand, expand. Both valves closed. When it expand, pressure go down, but volume go up, right? So it expand. After it expand, I open the suction valve. Okay, let new gas coming in. So this time when I open the suction valve, I take new gas coming in, so volume go up, but pressure stay constant. I complete the process. The area in 1, 2, 3, 4 indicate that compression work done. Okay, this area. If this area is big, we need more horsepower. If this area is small, we need less horsepower. That's what it is. Okay, different process cause us to move from one point to another point in PV diagram. Question? No question yet. Okay. All right. Look at the clearance volume. Look at this in number 3. What if I have 99% clearance volume? I push just a little bit, and then I do this. I didn't do much compression, right? I do just small compression compared to compress a lot. Okay, but I cannot go all the way. If I go all the way, I hit with the valve. Think about that. I cannot do it all the way. It's have to have some clearance volume, right? If I go all the way, I hit. I don't want that. So, but if I do very small, it doesn't do anything. So that clearance volume tell us about how efficient we are in terms of compression. Okay, if we have big clearance volume, it's not a very efficient process. We call that theoretical volumetric efficiency, E sub B. Okay, E sub B is the efficiency of compressor cylinder. It calculated by the ratio of volume of gas actually delivered divided by piston displacement. Okay. Here's the formula. Okay. So I put here, re-expansion has greatest effect on volumetric efficiency. re-expansion. So if you have a big gap, it's not good. Another factor, even when I look at this equation, how efficient I do it. If R is big, I have low volumetric efficiency. It's not good. So if CL is big or R is big, I don't have a good efficiency, okay? In terms of volumetric efficiency. So this means if I have a large compression ratio, it's kind of equivalent to push my piston just a little bit, just like do this, instead of go all the way, instead of go almost all the way, okay? All right, let's do some derivation. So, E sub V is gas volume pump per cycle. Gas volume pump per cycle is how much I pump per cycle. Is that volume, right? V1 minus V4. That's the volume pump per cycle. I don't give, even though I don't keep the exam on this thing, okay? And it won't be on the quiz, I promise, okay? It won't be on the quiz or the exam. I still want you to know. The part that I want you to know is, what is that CL? How do I get CL from this chart, okay? So even though you may not know the derivation, you need to know how to calculate CL, clearance ratio. Okay, let's start. Volume that we pump per cycle is V1 minus V4. So that is how much we pump per cycle. Divided by stroke volume of the cylinder. Stroke volume means C1 minus C3.5. This much is the stroke volume. So I deliver 1 minus 4, but the stroke volume has to push almost all the way. Alright? So that's stroke volume. And now we go back to our definition of polytropic process. Polytropic process, we have PV to the power of n equal to constant. N can be anything. If n is 1, it's isothermal. If n is k, it's isentropic. And in reality, we have something between isothermal and adiabatic process. Okay? So we know ratio of volume equal to V1 over V2 is P2 over P1 to the power of 1 over n. So this part comes from this equation. Okay, that's what it is. Then look at this. P1 and P4. Okay, is that the same? Yes. Pressure at point 1 and pressure at point 2 at pressure at point 4 is the same. It's on the same level. Pressure at point 2 and pressure at point 3, they are the same, right? So this means I can just write it like this. And from the same relationship, this relationship, PV to the power of n equal to constant, is for like expansion or compression, okay? Is for this curved part of the chart, not for the straight line part. Okay? So then I have this relationship, right? And I call this R sub V, okay? R sub V, ratio of volume. Is it compression ratio? Not really. Compression ratio is in PSIA is ratio of pressure. It's not ratio of volume. Okay, ratio of pressure is a compression ratio, but ratio of volume is not compression ratio. Then I know that V1 equal to VC. VC is that small gap plus this V, right? So this will give me volume at point 1. So V1 is VC, and that is I call V delta. So V delta. V4 is V3 multiplied by RV, volume ratio from this equation, okay? Or V4 equal to, what is V3? V3 is a volume at that point, which is the same as VC, trans volume, right? So I have this equation. Substitute everything in that. I have this, rearrange it a little bit, I get that. Okay, and now look, R sub V is not compression ratio yet. It is compression ratio over 1 over n to the power of 1 over n. Okay, if n is k, then I get that. So that equal to R sub B. And clearance ratio. Clearance ratio is VC over V delta. So VC is that gap. V delta is this part. Okay. V delta is the total stroke volume. Okay. This is the part that you need to know. When I use this equation, I have clearance fraction. It's not clear how I get that. It's not very clear, right? What is clearance fraction? What fraction divided by fraction? But when you look at the derivation, okay, you know it for sure that it is a gap divided by the total stroke volume. Okay, that's VC. So that's how we do the derivation for E sub V. At the end, you know the definition of CL, and two more things that you know is it's not good to have too big R or too big CL. Okay, but we always need some clearance so that the piston doesn't hit the wall. Okay. All right. Work required. The objective is to tell how many horsepower do we need to buy. Okay. Maximum theoretical horsepower, at most, in theory, the horsepower for receipt unit can be calculated from adiabatic compression process. Okay, adiabatic compression process. Reversible adiabatic is this line. Okay. And at least the minimum theoretical work for the compression is isothermal process. Okay, so we can calculate this line and that line. So when we say minimum theoretical work, it's really minimum work. The actual work is more than the maximum theoretical limit. Okay? The actual line is either this line or that line. Okay? So the actual one will be more than the theoretical value. Now, I want to know why we need less power, or we need less horsepower if we can do isothermal process. Look at this. If I have isothermal process, I have kind of less area under the curve, right? If it is adiabatic means I don't let heat escape. I have more area under the curve. What is that conceptually? What do you think? Okay. Any other explanation? How do I explain to anyone who don't want to know anything about the theory at all? How do I do that? Of course, with theory, I have the derivation and I can show you that, okay, eventually cooling it have less area or something. So if I have to explain to someone who don't care anything about the theory, how do I convince them? I would do this. Okay. When we heat it, when we compress it, temperature will go up and up and up and up. When it's too hot, it's not efficient. Okay? So if I can have isothermal process, this means I can compress when it is not too hot. Good? So when it is not too hot, I can compress it. Then it requires less horsepower, just that. Okay? That's for layman language. And I just say, okay, when I look at this compressor, I see at the back of compressor there is a big area cooler. Use air to cool it for interstate cooler. So this means cool is good. Just that. Okay. But you need to know more than that, right? Not just that. Alright. Adiabatic process, we assume that amount of heat transfer to gas or compressor cylinder and piston is very small compared to the work involved in the compression. So in theory, adiabatic means no heat in or out. But in this case, we may say, hey, the heat that coming in or going out is very small compared to the heat that involved in the compression process. So we may assume it adiabatic. It go a little closer to the actual line, but it's not the same, it's still less. Okay. Okay, let's review first law of thermodynamics a little bit more, and then second law, and then I think we are ready to go to do the derivation. First law of thermodynamics, I have W equal to Q minus W. W is internal energy, Q is heat added into the system, W is work done by the system. Okay. This equation tells me if I add heat into the system, Q, it have to either do some work or getting hotter. Okay. W change in internal energy is kind of change in the temperature, right? So when I add heat into the system, the temperature should go up, or it should do some work, or it's expand or something. Okay, that's the meaning of this equation. We cannot create energy out of nowhere. Okay, that's the first law of thermodynamics. Okay, intensity property and extensive property. This is just for you to know that when it is in the quiz or in the exam, you can be able to tell. Intensity property means the property, the thermodynamic property that is independent of amount of material. For example, pressure or temperature, that is intensity property. Memorize it. Extensive property is a property that dependent upon amount of material. For example, mass and volume. Okay? When we have more volume, this means we have more material. When we have more mass, it's more material, right? But when we have higher temperature, it doesn't mean that I gain more mass. Make sense? So, the rule of thumb over here is energy in general is a multiplication between intensive with delta of extensive. For example, P delta V, Q equal to T delta S or something. Alright? That's what we get from first law. This slide, you memorize that equation and these two, intensive, extensive property. What is that? That is some kind of language that you will see in the textbook, so if you know it right now, you don't get confused when you read more. Second law of thermodynamics. We have the equation ds equal to delta Q over T, reversible. So this says entropy is defined for a reversible process at T where Q is the heat absorbed. We don't really use this one, it's used more in physics. What we use is, from the second law, the interpretation is this. We do not have perfect heat engine. Okay? When we put heat into the engine, it has to release heat somewhere. Okay? It cannot just do work. I have compressor. I add heat in, add some power in, it just do work, 100% conversion from energy to work. Cannot happen. It had to generate some heat elsewhere. Okay? It is impossible to extract amount of heat QH from a hot reservoir to use it all to do the work W. Some amount of heat QC must be exhausted at a cold reservoir. There is no perfect heat engine. Right? That's what we get from second law. Okay, also this one. Any cyclic process, entropy will either remain the same or increase. It won't go down. Okay, for the cyclic process. Are we about to be able to use the Euler diagram again? Let's go to conservation of energy with some more math. Okay, steady state. Okay, steady state in SI unit. In SI unit, I have delta U, I have Q, and minus W. Same as the first law of thermodynamics. Okay, first law of thermodynamics over here is defined over the closed system. Okay, defined over the closed system. But this one is kind of first law of thermodynamics too, but it's not defined over the closed system. The difference between this slide and previous slide is there's mass in and out. Okay, it's steady state. Mass going in, mass going out, they're the same, but there's a mass coming in and going out. So that in addition to the increase in temperature or internal energy, it can have a change in kinetic energy, potential energy, or it may do some delta PV work. Okay. So this equation is for steady state case. It's defined over control volume domain. Mass can go in and out. Okay. Delta equal to out, defined as out minus in. So that is SI unit. For SI unit, Jeremy N. Bilisek is gone. Emily M. Billingsley. That's Emily. Hi Emily. What is the unit of Q for SI? You don't like SI. How about W? Work. Okay, in SI, what is the unit for mass? Emily? Kilogram, okay. How about G? Meter per second square. Okay. Multiply them together become Newton. Newton multiplied with length give us J what? Joules. Okay. So on the top one is joules. The unit of every term is joule. Emily, what about the bottom one? What is Q over there? What do you think? So unit of Q that we use in line heater is what? BTU, right? But okay, think about pressure. Emily, what is pressure? PSI. And volume is cubic foot, right? So pound force per foot square multiplied by cubic foot will give me pound force foot. So thank you very much, Emily. So this equation, every term must have pound force foot. The unit in this equation has to be pound force foot. Okay. Q, we cannot put it in BTU. If we know Q in BTU, we have to use this conversion. 1 BTU equal to 778 pound force foot. Okay. And same as work. Work has to be in the unit of pound force foot. Okay. What about this? M. This M in English unit is pound mass, right? Pound. What about you? Velocity. Velocity square will give me feet square per second square. I don't want this. So mu square will be pound mass foot. Not neither. Pound force or pound mass foot per second square multiplied by another foot, right? I have to do unit conversion, so that term become pound force foot. I use this G sub C conversion factor. Okay. So if I have something in pound mass foot per second square, I know that 32.2 pound mass foot per second square equal to 1 pound force. Okay. So I divided it by G sub C. Everyone now should be familiar with this. Good. Rohan, is this still confusing? Are you good? Alright. The reason that we have G sub C is not just like actual G, no, it's the unit conversion from pound mass foot per second square to be pound force. So that when it multiplied by another length scale, it will be pound force foot. All the unit in each term must be pound force foot. Okay? So that is in engineering unit. So in SI, that's G over there. For this, we divided by GC. So this, we divided by GC for unit conversion. Alright. For the horsepower thing, we cannot get the actual horsepower, but we can have theoretical prediction of the horsepower. Theoretical prediction of the horsepower that is close to actual horsepower. Is it isothermal case or isentropic? Raise your hand. Isothermal case. Raise your hand. Raise your hand. It's wrong, don't raise your hand. Isentropic case. This one is correct. This one is correct. So look at the diagram previously that we have. Isentropic case is somewhat closer to the real case, right? Okay. That's why we do ideal isentropic horsepower estimation. We start from steady state energy balance. We neglect the change in elevation. Is this okay? Neglecting the elevation term. Yes? If you look at the compressor in the field, it coming in maybe that tall and it going out maybe, is that going out? Probably. It doesn't have much change in the elevation, that's what I can say. It doesn't have much change in the elevation. It doesn't have much change in the velocity either. So I neglect the change in the kinetic energy. And I say it's reversible adiabatic. Reversible adiabatic means Q equal to 0. Okay? So I can delete that term. And instead of U, I combine U with delta PV. Then I have enthalpy. When I neglect all this, then I get enthalpy equal to minus W. W is heat done by the system. Minus W is heat done on the system. Okay? As per this definition. So this means if we add heat on the system, if we have work on the system, enthalpy go up. It's getting hotter. Okay. If we do some work on the heat system, it's getting hotter. Or if we compress gas, gas become hotter. That's what this equation tells us. Right? Isentropic horsepower we can use from modular diagram. Entropy S and enthalpy H. Okay, diagram. When I want to know isentropic horsepower, when I compress from one pressure to another pressure, I go up straight, just like that. Good. If you still recall temperature, the line of constant temperature is this kind of line. Okay, this kind of line from left to right or right to left, the horizontal one, that one is a constant temperature. Kind of vertical thing, or close to the vertical, that curve is constant pressure. That's a constant pressure line. So when I move from 1 to 2, then I read delta H. Then I can tell. Ideally, if I do the compression, how much heat will it generate, or will it become how much hotter? I can read the temperature directly. Okay, but we will tell you how to use the chart in a moment. So from this equation, delta H equal to minus W. So from the chart, we don't have capital H, but we have this thing is small h. Okay. Small h is molar specific enthalpy. Okay. One of them is at the intake or at the suction, and H2 is at the discharge. Suction and discharge. That's what it is. So work is related by delta H like this. Delta H is BTU. Positive enthalpy equal to negative work, or if delta H is positive, this means some work is done onto the system. Right? Totally, after you finish, let me see who missed the class, okay? Okay, modular diagram. Now you are ready to use a modular diagram. What is the theoretical horsepower consumed by compressing 1 million cubic foot per day, measured at 14.73 psia and 60 Fahrenheit? From 60 psia and ATF to 250 psia. Okay. When we say PSI A or standard volume. Okay. What is the standard pressure for Texas? Anyone know? It is not 14.73. It is 14.65. Okay. For Texas in particular, it's 14.65. But AGA handbook, American Gas Association, they use 14.73. Okay. So if you report your production to state, you use 14.65. If you report to federal, you may have to use another number differently. Okay. But this time, they show okay, it is that much and that much for standard pressure and temperature. I want to compress from 65 psi to 215 psi. First of all, how much is the compression ratio? Who has a calculator? Calculator. Yeah. Tell me, how much is 215 divided by 65? 3 something. 3.3. That is the compression ratio. Okay. So discharge divided by intake. Okay. We will start from ATF. We compress it to 215. Okay. Assume the gas gravity is 0.6. What is the temperature after the compression? How do I know that? I read the chart. Okay. So this is a model diagram. And 700 Fahrenheit line is on the top. Okay, that's a constant temperature line. 32 line is over here, kind of S shape. When you do the test, you will get the actual chart to use. It will be larger. So when I do the compression, I move from here up straight. Look at this. I go from here, which is the cross point between 80 Fahrenheit. 80 Fahrenheit, I found that it is this line. That's 80 Fahrenheit. And 65 psi is that line. Okay, that's 65. I go straight up. Mobile, what's that? Why do I go straight up? What is straight up? What is that green thing? Which parameter is constant mobile?
Temperature?
Not temperature. When we compress, the temperature go up. I'm sorry. What's the constant? Look at the axis. What's that mobile?
The what?
You cannot see this?
I don't see.
Come to sit in the front. Can you see it? Yeah, you can go back. So when we go straight up, so that it is constant entropy, constant S. So we have constant entropy process. We are doing theoretical horsepower calculation, right? Or theoretical compression thing. So theoretically, when we do the compression, we assume constant entropy, right? Good? So we assume that we go straight up in theory. Everyone signed the sign-up sheet? Already? Can I have it already? Yeah, sign-up sheet. Or you are not done with counting number of students? Huh? Oh. Who haven't signed it yet? Jeremy Bisek, not here. Next one, Ivan Garcia, not here. Eric Tess, Eric, no, it's not here. Levi S. McCurdy, no, not here. Daniel G. Martinez, not here. Beck Martin, not here either. Stephen Lee, no, Stephen Lee. Alexander Crow, not here. So what do you get?
So I got
More signature than the number of people?
one more. Yeah.
One more people than the number of signature. I don't like that. Okay, let me go real quick. Rohan and Rowan. Okay, raise your hand. Simon C. Achoku. Raise your hand. Okay, good. Alfshin Oliver. Okay. Foster R. Anderson. Okay. Mobile. Over there. Sterling R. Sterling. Okay. Oliver Miller W. Benny. Okay. Ryan L. Baxter. Ryan L. Baxter. Baxter. Okay. Clara Benavides. Clara. Okay, that's Clara. Jeremy Billingsley. No, not here. Emily Billingsley. Okay. Connor P. Black. What's this? Gnamin. Bene. Benedict, right? Okay. Carson B. Boy. Carson B. Boy. Okay. Landon H. Breeding. Stuart W. Bruce. Brian J. Bucco something. So that's you. Okay. Richard Bumate. Okay, Richard Bumate. Graham H. Bunting. Alina C. Carter. Okay. Taylor Cooper. Scott M. Curtis. Jacob A. Dele. Taylor M. Davis. Hamza. Okay. Jared Eddie. Karim. William W. Esther. Paul Everett. Ivan. Oh no, he's not here. Ryan Gavlas. That's you? Okay. Brandon Gillespie. Okay, that's Brandon. Matthew Voigt. Voigt. Okay, that's you. Carol R. Harrington. Suleiman Hasanoff. Suleiman Hasanoff. Oh, okay, I'm sorry about that. Okay. Hayden A. Hart. That's Hayden. Lawrence B. Hess. Okay. Alina Duplantis. Shane Clarence.